actual distance, do we even have to solve for that?
I think I have to give you, let me take a look at it again.
Because don't you need like a distance between the wires to solve numerically?
I think if this was given on a test, it was given on a test.
But he also uploaded a corrected thing on Blackboard.
Yeah, but no, this is an older version. This is a test from a while ago.
Oh.
And I think what I did here was they go, well, you need the distance between the wires. And I go, okay, you're right. Fine.
Gotcha.
A meter. There you go. Leave me alone. And
Thanks.
so you're welcome. All right, this is test 2 review for 214. It is 20%. Just as a reminder, SDS students need to meet in the lab. They'll start at 8. If you're late, then go to the lab and then you just sit on the other side of the room and you finish on time. We typically, we'll have like 20 of them because the room physically can't hold everybody. It's 20% of the total. There are 25 multiple choice. There is one appetizer with a 100% metaphysical probability that it is the right-hand rule. And it's the right-hand rule where sometimes it'll be one of the first 2 vectors that are missing rather than the third. Just to make, you guys are 214, you're a little bit stronger, so you get a little bit harder problems. So you got the right-hand rule game. I don't want to make that a free 5 points. And then there are 3 problems. 100% metaphysical probability is Kirchhoff's law. Two, there's another, magnetic induction. That's also 100% metaphysical probability. Problem 3, it's a 50-50 split between B-field addition and particles in a B field. So it's going to be a 50-50 chance. If it ends up being B field additions, then you know the coin showed up heads. If it's particle, then it was tails. The test has not been written, so there's no point in you guys kidnapping me and holding me for ransom by releasing the problems because I don't know what they are yet. And that's it. That's the test. How hard can that be? It's a little bit harder. In my estimation, for the first 4 years I taught this, I said that test 2 of 214 was the hardest test that you would ever take in pre-med physics. For the last 2 years, the 2-3 years, the students have said it's not that bad. They always say that the final just crushes their will to live, but other than that, so that's it. The B field induction, I don't know if it's the circle or the moving bar. I'm not sure yet. Once again, that's a head tails flip. And so that's it. So I guess I can open the floor to questions and then we can talk. Yes.
Can you do a particles in a B field?
Particle in a B field. All right. For this, it really asks that you understand rotational motion, because particle in a field would be something like you have a particle moving with velocity v, you have a B field, let's say into the page, the particle is positive. If the particle is positive and the B field is in, does it bank left or right? So the magnetic force is Q V vector cross with B vector. V cross B, thumb points left, which means that the magnetic force is that way. So what it will do is it will bank like that. Now, this could go several different directions, one of which is what's this length or this distance d that this thing moves. Really what's happening is that it's moving in a semicircle. There could be situations where it does move in a full circle, but it's like if this room had a B field in it and we had no gravity, well, first off, we'd all be floating around. I'd let the class play for a few minutes because, dude, no gravity. But then if I threw a charge in a particular direction, it would start moving in a circular motion and stay that way. If there was no, and if with air friction, it would eventually slow down. But if there was no air, well, we'd all die. But that thing would then continue in a circle forever. In circular motion, the sum of the forces is equal to mv squared over r. For circular motion, it's mv squared over r. In linear motion, if it doesn't accelerate, then it is just 0 or ma. But because it's circular motion, that radial acceleration is v squared over r. And this equals qvb. So one of the v's cancels, and now I've got mv over r equals qb. And then you could get all sorts of variables out of it. If I said, well, give me the distance d, well, d is equal to 2r, or d over 2 is equal to r, or in this case, since it's in the denominator, 2 over d is equal to 1 over r. So then this becomes 2mv over d is equal to qb, or 2mv over qb is equal to d. So it's a lot of this is algebra play with looking for particular values. If I said, well, what's the time that it took to travel from there to there? Well, you know, velocity is the distance divided by time. This particular case, the distance is a semicircle, or pi r, because it's half of a circumference, and there's the time. If I gave you the velocity and I said, well, what's the time for this? Then velocity, or actually, I'm sorry, t is pi r over v. And then you can get the time that way. If I asked for the period of the motion would just be a full circle, and then you would use just 2 pi r over t, solve for t. If I just had, let's say I had a particle moving in a circle, and I wanted to know the B field, I would have to give you the period. Let's say the period was 20 seconds. The velocity was 400 meters per second. Let's see what we could get from this. The circular motion says that mv squared over r is the sum of the forces, and that is equal to qvb. May end up needing r, just a second. If I do need r, let's say it is 50 meters. So then mv over qr is equal to b. I would then need the charge. Let's say charge is 1 microcoulomb, and its mass, see, I would have to give you a lot of different things. The mass is 1 times 10 to the negative 3 kilogram. So the mass is 1 times 10 to the negative 3. The velocity is 400. Q is 1 times 10 to the negative 6. R is 50. And that gives you, may not need period. That gives me a B field of something. So 8,000 Tesla, which is really high. I'll try to make the numbers a little bit more sensible. And as an example, it's what I told the 213s. In addition to helping you solve problems, Alphabet Soup is superior. In doing problems that involve writing the problem and putting in numbers that you want to work out, this is the way that I would do it. I would sit there and just chug the numbers in. And probably what I would do is I would say, ooh, 8,000's too high. I'm going to cut the velocity and increase the radius. Or increase the charge. So you could be able to get all sorts of things out of that. So know your basic circular motion. Now, the thing won't accelerate. Oh my goodness, accelerating charges in a magnetic field. No, it won't do that. But what it will do is, then you got to notice the basic things of moment of inertia of a particle in a magnetic field is mr squared. Know that angular momentum is I omega. So look at test 2 rotation. From 213 and look at where alpha is equal to 0. It's not that much, and the equations that you need, if it's on the test, will be in the equation section. But the problem that I would do is particle spectrometer. And start doing that. Looking over that and knowing the basics of the velocity selector. But this would be the guy for circular motion. So that's anything more specific about something like this, or? Yes.
Like on the test, it's gonna be a diagram like the one on the left or the one on the right? Or are those two different
Yes.
things?
Probably it could be either one. It could be a particle just sitting there orbiting, or in a situation like this, if there was no wall right there, it would just go on forever. So I'm limiting you to a full circumference. Here I'm limiting you to half a circumference.
Okay, and what's the difference in equations? Like,
Not really, nothing much. Yeah, nothing much. Here the time would be just half a period, since it wouldn't be able to go around in a full circle. Here, the time that I would deal would be the full period.
and the last question, what's that, A R equals B squared over R?
This is radial acceleration. So when you have Newton's second law, sum of the forces is equal to ma, that ma is radial acceleration. Radial acceleration is v squared over r, and so that's where mv squared over r comes from. Okay. Yes.
What if you have like a wire and then like if you go like to the left or to the right? You know, so
Are you saying like
yeah,
if the current is this way, is the B field out or in? Would that be something that you would ask? Okay. Let's say, for instance, that I was 20 milliamps, and I'm at a particular distance, R, which is 3 meters. What is the B field, and is it in or out? So the B field magnitude, in or out. We're only dealing with one of two major, three major things. Arc, circle, line, or a combination of a circle with a line. Here we just have a line. So the B field is magnitude-wise mu naught I over 2 pi r. So for a line, it's like that. For an arc, it is mu naught I theta over 4 pi r. And for a circle, it's mu naught I over 2r. Now for the arc, it's at the center of the arc. For the circle, it's at the center of the circle. If I have a line with a circle, the only place that I could reasonably expect you to know what the B field is at the center of that circle. So the B field,
You wouldn't have like a bar and then a circle.
I could.
That's what I'm saying. That's what I'm.
Oh, okay. Let's do this then. So I want to know what the B field is at that point. And the thing that I would do with this is I would say that,
Yeah. Clockwise.
oh, hold on. Counterclockwise. So for something like this, the green is the linear current. You do the wrap rule. Anything on the left side is out of the page. And actually, I'm gonna change my mind, just because it makes it more interesting. The current is running clockwise. The current in the line is running from bottom to top. For the green line, stick your thumb in the direction of the current for the wrap rule. Fingers come out on the left side, they go in on the right. Any point on the left is out, including the region inside the circle. Now the circle has its own current. It's going clockwise. To get that, the red line for I2 is going in. Now let's set up some distances. The radius of the disk is R. The distance from the edge of the disk, or not disk, circle to the line is D.
Can you explain why you know that that's
Okay, hold on. Let's draw it a little bit here.
What kind of problem is this?
Magnetic field addition. Oh, I'm switching the colors. Oh, deal with me.
Can you draw it again?
Can I what? Can I draw it in different colors? I only brought blue and aqua as well as black. I don't have much of a choice. There was a student who came in and asked a question in my office yesterday, and so I said, go to the board and start working. And she demanded that she use every single whiteboard marker I got. And I have 12. It looks like she ate a Crayola box and then vomited back on the board. It was horrific. I know. How do I know what the B field is doing because of the green current? which over here is the red current, but let's not judge. The current at the bottom of this circle is heading left because it's going in a clockwise formation. Put your thumb in the direction of the current at that point, and what you notice is the fingers claw in above the line and claw out below it. So it's like that. If you did it over here, the thumb would be up, your fingers again claw in, and then claw out on the outside. So it's the same thing. So the total B field contribution is positive from the line and negative from the circle. So it becomes B total equals positive mu naught I1 divided by 2 pi R1. I'm using weird units, but let's deal with it for just a moment. And then this is mu naught I2 over 2R2. Now in this particular case, R2 is equal to R, the radius of the circle. So this is mu naught I2 over 2R. But the distance from the center of the circle to the line is D plus R. So this is positive mu naught I1 over 2 pi R1 plus, R plus D. And that is the total magnetic field. Yes?
Can you go over how you found the signs again to put in the equation?
Okay. "30-second rant. We live in a cursed right-handed world. They demand that identity is true. That X hat cross Y hat is equal to Z hat. We're familiar with the typical 2D coordinate system. So if X hat cross Y hat is Z hat, X cross Y, Z is out of the board. So Z is out. So positive Z is out of the page and negative Z is into the page. If the B field vector is in, it is negative. If the B field vector is out, it is positive. Now over here, the B field wraps. So the B field from the line on this side of the wire is negative. On this side of the wire, which is the same side as the center of the circle, it's positive. For the green line, it is clockwise. And as I've demonstrated before, if you put your finger in the direction of the current at that particular point, your fingers claw into the circle because of the circular current, and when you wrap it around, it comes out underneath. So at this point, which is the only point I care about or will ask about if I've got a circle involved, it comes out of the page, it goes into the page, so that part is negative. So the B field contribution from the circle, which is this part, is negative. The B field contribution from the line is positive. And that's it. Yes?
The circle is on the other side of the intersection. Or would one of them?
If the current was still clockwise,
Yeah.
the B field would be in for the circle and it would be in for the wire. They wouldn't, yeah, they'd both be negative, correct.
So you can have a negative B field at a certain line,
Yeah,
B total.
yeah. The only reason why I love having the B field equal 0 is that I can dump mu naught, which is 4 pi times 10 to the negative 7. Why do I know it? Because I've said it 1,000 times. I don't expect you to know it, but what I do like to do occasionally, if I set it to 0, if I set this is equal to 0, then that goes over there, and then a mu naught and a 2 cancel. It simplifies. And so I'm a big... so many people go, you must think all professors lie, probably, except for me. I love doing these zero-type magnetic field problems because I hate writing all these equations. And so I like simplifying it.
What's the bottom formula for? Bottom of B.
This is the total B because R1 is R plus D and R2 is R.
Is the top also B total?
Yeah.
Alright.
But this is, I expressed it as R1 and R2, and then I defined that R2 is R, and that R1 is D plus R. So that's it. Yes?
How do you know if you can set it to 0 or not?
I would have to tell you. I would say the B field at the center of that circle is 0. Give me either I1, R, D, or I2. So it'd just be a mathematical manipulation. Because we all know how much I dislike numbers, except for 0. 0 is the man. So.
Why is the left side of the wire not given in the equation at all? Like the straight.
For this, the left side does come into play because it's out of the wire, so it's positive. Restate your question again.
I don't know. I didn't read right, sorry.
Okay. If I said, what is the B field only of the circle, it would just be this. If I would say, what's the B field only from the wire contribution at that point, it would only be that. What's the total? Boom. Put the two together. Put together what you got, bibbidi bobbidi boo. I got to keep myself amused for this.
So you wouldn't ask for outside the ring on the test?
No. If I did, I would expect you to know you would be in Physics 212. Probably Honors 212. Normal 212 students are. I think a lot of you guys would beat 212 students in a straight up test. I would love to exchange tests with 212 and just say no calculus, and I still think you guys would do better. Next question. I will not answer what's on the test. Well, honestly, I will answer that. I don't know. I haven't written it. So, I will, go ahead. What's your? Oh, you want the induction with the change in area? Okay. I will say this, I've cleaned up the multiple choice so that oh no. So you won't get stuff like which one is in and which one is out. I think that's kind of obvious. I took that away. I took away. So.
Will you post more multiple choice?
We're running out of time. I don't have the time. I think I could barely post the solutions for. You know what? I think I may go. Let me dig through an old class, and I may have done it and posted it there, and I'll just copy and repaste it.
Repaste what?
Solution sets to old 214 tests that I may have done earlier.
Yes, sir.
And a lot of this is critical upon. I gotta write the 214 test, proof it, and print it before I go home tonight. So I'm focused on that. If it gets to that point and it's 7 o'clock at night, I'm out. So the velocity of the bar is right. Now, if you look at the examples that we did in one particular lecture, you can't say the velocity is to the right therefore the magnetic force is to the left. You just can't straight up and do it. But if you do the logic and that magnetic force isn't opposite of velocity, you've messed up. So the B field, let's say I give it to you and it's out of the page. That means that the magnetic flux is coming out of the page as well. Now, in situations that we've talked about this, and this is kind of a new thing that I've thought of, makes sense when you think of it. If the velocity is to the right, area increases and d phi b dt is parallel to phi b. Because if the bar is going to the right, the area is increasing. If the area is increasing, more wind is getting through in the direction that it's moving initially. So in this case, the B field is up, the bar goes to the right, the area of the window increases, so more flux is coming out of the page, so d phi b dt is out of the page. The induced B field and the induced magnetic flux, due to Lenz's law, is always anti-parallel to d phi b dt. This? The induced, this aqua, this is an aqua. See, I'm using all my colors. I don't like, now actually, I mean, here's my moment rant while everybody's absorbing this. The 1.0 millimeter pens commonly at Walmart are only in black, red, green, and blue. I prefer the 1 millimeter because it's a thicker and it's a smoother draw. Everything else comes in 0.7 or 0.5, and aqua, you have to go on Amazon to get it.
Is that the
Phi sub B and B sub end. These are induced. The one problem that I don't like about the overhead projectors is that they don't really show color all that well. This is why I think, tell your friends on the 213, 214 this summer, I'm going to be in 101, I'll be using whiteboards. And so what I'll be doing is if I'm not here in the fall, I will make my last stand of lectures and try to be as detailed as I can, and just then the last lecture I just drop the whiteboard marker, roll off set, and then turn it off. And there we go. And I'll ride off into the sunset. Yes?
Could you explain why the d phi b over dt is out of the page again?
V is to the right. Therefore, is the area that the flux can go through, is it increasing or decreasing? It's increasing. So the area of the window is increasing, so more flux is getting through in the direction that it was coming through initially. So it's BA out, and then the area gets bigger, so now it's a bigger BA out. So that d phi b dt has to be in the same, it must be in the same direction as, if the velocity was to the left, the area goes down and d phi b dt is anti-parallel to phi b. Because smaller window, less wind getting through in the direction that it was headed, which means you can think of it as a wind going in the opposite direction.
Kind of like pressure thing.
If V goes to the left, let's do it in the other way. Okay. If V is to the left, area decreases and d phi b dt is anti-parallel to phi b. But in this case, the velocity is going to the right, which means that the induced flux, because it is opposite of this, that induced stuff must be in. And the only way that you can get an induced flux to go in is if the induced current is clockwise.
Will you do a Kirchhoff's law?
Okay, we're not done yet. Okay, go ahead.
Is the current going through the bar the same as the current going through the loop?
Yes. Because really, let me tell you, these are infinite lines that never join to the right. So this bar completes the circuit. And if you look at it, the bar goes from top down. I cross B, magnetic flux, or the magnetic force is to the left.
Say that one more time, I'm sorry.
I is towards the ground.
Right.
B is out of the page. So the magnetic force is to the left.
And you'll always have B coming out of the page?
Not necessarily.
Okay, so if it's into the page, then magnetic force the other way. Okay.
Well, actually, the magnetic force would still be opposite of velocity. Because what? Do this. In lecture, I did all 8 permutations and talked about it. Find that video, and then you can go through everything.
Yes, sir.
So. All right. So we have a request for Kirchhoff's.
Can I ask you one more question?
Yes.
For one of those, you would have to say like d over dt equals 0
B over dt
or yeah.
is 0 in this case.
dB dt in this case is 0.
Would you have to give us that, or how do you?
Well, it's a moving. It's my promise to my students that only the B field will change, hence a circle, or the area changes, hence a bar. Once again, I would love to give a combination, but you guys would start crying. So and there isn't enough tissue on campus. Plus, it's from the lowest bidder. It's like sandpaper. It'd be horrible. Yes.
Is there a different way to write magnetic flux? Because in my notes I have it written different than the way you wrote it up there.
Magnetic flux typically is.
Induced flux, my fault.
Induced flux, sometimes I would probably write B sub I N D or phi sub B I N D. I'm not very particular. Typically, I just differentiate it through color. All right.
Doctor,
Yes.
you said the induced current has to be clockwise to get the induced stuff to go into the page?
To get the induced into the page, it has to be clockwise.
Is that just like, what do we cross?
Well, I know the induced has to be into the page. I only have 2 choices, clockwise or counterclockwise. If I know that it's clockwise, and the way that I can prove it is in this segment, the current is going to the left. So I put my thumb in the direction of that current and I claw in above and claw out below. That's clawing in above. So that's how. Now, Kirchhoff's law. The brute force Kirchhoff's law typically is, I want to set this up so that R1, R2, R3. R3 is 50 ohms. R1 will be 40 ohms. And R2 will be 10 ohms. V1 will be 20 volts. V2 will be 30 volts. The question for all of this is, does the current through R2 go up or down, and with what magnitude? That's it. That's all I want to know for the Kirchhoff's law. That's enough. What you do is you set up two loops, two dummy currents. The dummy currents I call J1 and J2. The dummy currents, J1 and J2, always go clockwise. Always, always. Then you set up two loops. One loop for each box. You may choose to pick whatever corner you like to start off with. I typically pick the left lower. Why? I don't know. I'm just consistent that way. And I set up two loops, and I know that if I walk each loop, loop 1 and loop 2, I know that the delta V for loop 1 will be 0, and the delta V for loop 2 would be 0 as well. If you start and finish at the same point, the change in potential will be 0. That's it. So you walk the loop and you note the potential differences. J1 travels exclusively through here, here, there, and there. J2 travels exclusively through here, 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 and there. So there is only one segment where both currents are going through. That's the R2 segment. Walking the loop from there to there, I'm traveling with J1 across R1. So 0 equals minus J1 R1. I then go from a positive to negative lead across V1, so it is minus V1. In the middle loop, or in the middle segment, J1 is going down and J2 is going up. If I go from top to bottom, I'm going with J1 but against J2. So that is minus J1 R2 plus J2 R2. And then from there to there, there's nothing, so I don't worry about it. Simplifying this, I get minus J1 R1 plus R2 minus V1 plus J2 R2. And that's a simplified way of doing things. For loop 2, you start from there to there. You're going from bottom to top. You're going with J2 but against J1. So this is minus J2 R2 and plus J1 R2. I then go from positive to negative across a second battery, V2. So minus V2. I then go with the current J2 across R3, minus J2 R3. And that again is equal to 0. Simplifying it, 0 is equal to minus J2 R2 plus R3 minus V2 plus J1 R2. And these are the circuits that I'm dealing, or the equations that I'm dealing with. It's a 2 equation, 2 unknown. J1 and J2 are the unknowns. Yes?
For loop 1, why is J1 R1, why is that one negative?
J1 is the current on this side, which is going from bottom to top. When you go from there to there, you are traveling with J1 across R1. Therefore, the change in potential drops. And that's it. Now, it's a 2 equation, 2 unknown. What I typically do for something like this is R1 plus R2 is 50. So it's minus 50 J1. V1 is 20 minus 20. R2 is 10, 10 J2 equals 0. The common factor is 10, so it's minus 5 J1 minus 2 plus J2. Really, what I do when I write these Kirchhoff law problems is I put a common factor into the numbers, just so it just makes things easier when you get to the 2 equation 2 unknown part. So 0 equals minus J2, R2, R3, 10 plus 50, so minus 60 J2 minus 30 plus 10 J2. Common factor again is 10, so 0 equals minus 6 J2 minus 3 plus, that's a J1, plus 10, plus J1. Now it's a 2 equation 2 unknown, and you can sit here and just figure stuff out. 6J2 plus 3 is equal to J1. Why did I choose that? I don't know. I just picked. But I solved for one of the variables, and I'm going to plug it in here. So minus 5, 6J2 plus 3, minus 2 plus J2 is equal to 0. All I did was take that and plug it in there. Now solve for J2. Minus 30 J2 minus 15 minus 2 plus J2 is equal to 0. Minus 30 J2 plus J2 is minus 29 J2. Minus 15 minus 2 is minus 17 is equal to 0. So minus 29 J2 is equal to 17, or J2 is equal to 17, or minus 17 29ths. Which gives me 0.586 amps negative. So J2 is a negative value. This means I2 is 0.586 amps counterclockwise. And now you know the value of I2, the current running, true current running in the right loop. The next thing, you've got J2, plug it in here, 6 minus 17 29ths plus 3, and that will give you negative 0.517 amps, which means I1 is equal to 0.517 amps counterclockwise. Since both are negative, I1 is going counterclockwise like this. J2 or I2 is also running counterclockwise, so I write it like that. The currents are running head to head, which means what I'm going to do is I'm going to take the magnitude of the bigger and subtract from it the magnitude of the smaller. So this becomes, I identify that I2 is bigger than I1, because 0.586 is bigger than 0.517. If I2 is bigger, then the current going through R3 is from top to bottom, or downward. The magnitude is 0.586 minus 0.517, and that is 0.069 amps. So the answer is 69 milliamps from top to bottom. Done. And that's all you would need for this. There are many ways to do this, but the way that I've determined it is one of the few times where I militantly require you to do it in a specific fashion. Yes?
Are you going to be putting up the video from the presentation on YouTube?
Unfortunately, the people who are in charge of the digital support are horrible, because what they did is the overhead projector was not working, and so we did the whole thing on the board. Because of that, I was unable to record it.
What about the multiple choice then?
The multiple choice, I will get around to posting. So, yes.
Could you put a capacitor on Kirchhoff?
No, I will not put a capacitor on Kirchhoff's. How dare you? I will think about it and I'll go, no, they'll just start crying.
I mean, would it mess everything up?
Yes, it would make things horrible. Well, yes, I'll just say yes. It will make things horrible. If he says capacitor and a Kirchhoff's law problem again, you have my permission to slap him. Yes. It depends. If it is, if I have it set up where it's a positive negative, where let's say the left was positive or clockwise, and the right was negative or counterclockwise, you know for a fact that this is going top down. So you would just add the magnitudes straight up. If I was doing this problem, I would be praying for a plus minus, because that makes it easy. With a double positive or a double negative, I gotta think about it. Question over here and then over here. Question on this side. Going once, going twice. Question over here.
I was just going to ask one.
No, not you, her. Then you. Because she had her hand up the whole time and then you interrupted. Yes. The first page? Okay. See, had I answered your question first, I would be rude to her. So I'd much rather have you angry at me for just a few seconds. Oh. Well, what's your question?
You answered it. That's why I was that's why I was telling you that you answered it.
Oh. So it wasn't a question, it was just a statement. Okay, fair enough. I was looking for questions, not statements. If you want to just praise me outright, just say it. Over here, right towards the middle.
So, or like the multiple choice that we went over in class on Tuesday.
Yeah.
For one like number 11 where it asks like the field from your position, can you explain to me that field?
Hold on. In fact, hopefully I can kill two birds with one stone on this. I know this makes great video. I thought I had a copy of this. Wait. Last effort. No, I don't have it. Can you give me your, what does it say?
There's a wire with current from field and cord stretched out to the B field vector and the wire at your position is.
Oh, so you're standing in front of this. Bye. So the current is going from top to bottom, which means that if you do the wrap rule, the B field is going away on the left and coming at you on the right. This is from the front. But if you look at it from the top, that left part deals with the vector in that direction. On the right, it deals with a vector in that direction. So it goes in like a circle. And at your position here, the B vector is going from right to left. So the B field at your personal perspective, your point, if you look to the left of the wire, the B field's going away from you. If you look to the B field on the right of the wire, it's towards you. But at your specific position, it's from right to left. Towards the back.
I have a question about something that you mentioned on the multiple choice section on Tuesday. You asked about the units for capacitance, and that's a farad. And then I think you said what is a farad times an ohm, and it equals a second.
Yes.
How is that? Like, what's that?
In problem 1 of problem set 6, I asked you to prove that. And there was, I think, if you look at the tutorial from last Friday, and that was the first thing out of the gate I did. I think we're done. Going once, going twice. I'm gonna put these videos up in the next hour or so.